we're considering chemistry, that is basically the behavior of electrons in systems where they're bound together with nuclei in these complex structures, we ought to consider first what we know about the electron as an independent entity. So how do we know electrons exist, and how do we know what properties they have? Electron, spelt with a K, is the ancient Greek word for amber. And before we had balloons, amber was the standard thing for rubbing in your hair to generate static electricity. So electricity essentially means that weird thing that amber does. It's not an ancient Greek idea. They didn't distinguish it from ordinary magnetism. The term electricus was invented by the English scientist William Gilbert around about 1600, and the word electricity first appears in 1646 in the writings of another English scientist, Thomas Brown. And from about that time onwards, people started to do all sorts of experiments with electricity. It seemed to behave like a fluid in many ways, but instead of doing what a fluid like water would and going downhill, it flowed towards places of opposite charge and flowed away from places of the same charge. So you could have two charged balloons sticking to the wall, say, but repelling each other. There wasn't an immediately obvious direction like down to describe the way electrically charged things moved, so the terms positive and negative for the directions of charge flow were set arbitrarily by this guy in the rebel North American colonies. There's nothing inherently negative about the electron. Electricity seemed to obey the inverse square law, like gravity. The force between charged things fell off by the distance between them squared. And the French scientist Charles Augustin de Coulomb confirmed this with an accurate new torsion balance he developed, so the relationship about the forces between two charged things is called Coulomb's law. Here, Q1 and Q2 in the equation are the charges on the charged things 1 and 2, and R is the distance between them. If we express these charges Q in the SI unit of electric charge, which is called the Coulomb, and R in meters, and F in newtons, then the constant of proportionality is related to the speed of light, c. So it'll be c squared times 10 to the minus 7. And the equation becomes that equation there. This rule applies to big charged things, little charged things. No matter how small a charged thing we've got, this rule applies to it, and we'll meet it again later. The form of energy known as work is force times distance, so we can also express the potential energy between two charged things by taking this force and multiplying it by R. So we can write this equation here using V for potential energy. And voltage, which we can also write V, is defined as energy per amount of charge. So if we have a moving charge thing, Q1, and a stationary charge thing, Q2, then we can express our voltage by this equation here, where E is something that we define as the electric field strength. Now, lightning or rubbing pieces of amber with rabbit fur are both really impractical ways to get electricity to experiment with. And the first practical way to get electricity to experiment with was through chemical reactions. And the first person to do this properly was Alessandro Volta around about 1800. He put alternating discs of copper and zinc in salt water, or dilute sulfuric acid, and connected the discs with wire, and found electricity flowed through the wires. And this is still the basic construction of all wet cell batteries. As well as generating electricity by chemical reactions, it was found out pretty early with apparatus like this that you could use electricity to drive chemical reactions. So if electricity was passed through a solution of water, it could be induced to decompose. If electricity was passed through molten salts of various kinds, intriguing new substances, never before seen, like aluminium, could be generated. So clearly there was some sort of fundamental connection between electricity and chemistry. Now, other fluids that we know of, like water, are made up of tiny bits of matter. And when you think about it, there are only really two possibilities if you've got some sort of stuff. Either there's the tiniest piece of that stuff, or there isn't. And both of these are really mind-blowing possibilities if you think about them. You just end up staring at your fingernails for hours thinking, wow, matter. Assuming there was such a thing as a smallest piece of electricity, this hypothetical piece of matter that is the tiniest bit of electricity you can get was named an electron by an English scientist named George Johnston Stoney in 1894. It was not demonstrated conclusively that there actually was such a thing as the tiniest piece of electricity you could get for another decade or so, and even now you get crazy physicists in places like New Scientist claiming they've done experiments that have split the charge on an electron into 3 equal parts. One important piece of evidence that these pieces of matter existed was discovered when it became possible to enclose things in glass and pump nearly all the air out. When electricity was passed through one of these newfangled gadgets, that is, through close to nothing, a vacuum, a pretty glow was observed. The pretty glow was not the important piece of evidence. That evidence was this. The glow seemed to be coming from one electrode and going to the other electrode. You can see from the picture here that the cathode rays, the rays generated in this cathode, are casting a shadow. So either rays of something like light or little glowing particles were coming out of the cathode and going to the anode. And unlike light, these cathode rays were affected by magnets. So this was a strong indication that they were little moving electrically charged particles, since it was known that somewhat larger electrically charged particles were also affected by magnets. This phenomenon is the basis for the cathode ray tubes that were used in televisions and computer screens until not so very many years ago. So if you've got an old television laying around, you can verify that the glowing particles making the picture are affected by magnets. Though this can leave permanent blotches on your screen, so don't do it unless you've got a newfangled liquid crystal screen you can use after you've stuffed up your old cathode ray tube. A German physicist, Eugen Goldstein, found that there were other rays traveling the opposite direction in the tube, which he called canal rays, because they had to go through holes or canals in the cathode in order to be detected. Both sorts of rays were affected by magnets and electrical fields, and the results were consistent with the cathode rays being negatively charged and the canal rays being positively charged. And while the exact properties of the canal rays were curiously different depending on what the cathode was made out of, the cathode rays were always the same. It was an Austrian physicist, Philipp Lenard, who figured out a way of getting cathode rays out of vacuum tubes by making tubes with very thin metal windows in them, so experiments could be done with these cathode rays. And this fellow found that these cathode rays were scattered strongly by air, which suggested that they had a very small amount of kinetic energy relative to the individual air molecules, so that they were likely to be very, very small. And he found also that these cathode rays were absorbed by various substances to a degree proportional to the amount of mass doing the absorbing. And only that. They weren't absorbed specifically by anything in particular, not like visible light or ultraviolet light and infrared light, which are all absorbed specifically to give us pretty spectra. And he also confirmed that the rays were affected by magnets and electrical charges once they were out of the tube. He called these things quanta of electricity, and by the time he had done enough experiments to win a Nobel Prize in physics, he had pretty well established that these were the smallest particles of negatively charged electricity you could get. But what exactly was the charge on these things? And what was the mass of these things? By examining the scattering of cathode rays more carefully in air, the English physicist J.J. Thomson estimated that they had to be about 100,000 times lighter than air molecules. And he calculated an estimate of their charge-to-mass ratio. We can show how he did this using our expression that we had before with electric field strength in it, and Newton's definition of force. Force equals mass times acceleration. So we can equate this to find out the acceleration an electron will feel in an electric field. It's that expression there. And you might remember this other expression for the distance covered by something accelerating at a constant rate. I think I did that back in year 11 physics. So Thomson generated these somethings going in one direction from these cathode rays and worked out how fast they were going, then applied an electric field perpendicular to that direction. And the distance, the spot where the somethings ended up on the target, so they've reacted with something on the target there, from where they would have been without the electric field, can then be given by this expression here. That's just combining those equations we've got before. When Thomson did this experiment, he found a charge-to-mass ratio, this bit here in the equation, that was about 2,000 times greater than the hydrogen ion, which was then the thing with the largest known charge-to-mass ratio. So this suggested either that they had a much greater charge than anything else, or given the results of their previous measurements scattering in air, that they were a lot smaller than anything else. And Thomson called these things corpuscles. Now, the final piece of the puzzle to tell us what an electron is was an experiment that was done by Robert Millikan, a physicist in the rebel North American colonies, which gave an estimate of the absolute value of the charge on these little corpuscles. In his experiment, he took little droplets of oil and gave them a negative charge and allowed them to drop at a constant velocity, and then pulled them up at a constant velocity using an electric field. So going down, the terminal velocity of these drops will be the force due to gravity divided by the coefficient of friction of the drop. So they're not dropping in a vacuum, they're dropping through air, and going up, the terminal velocity will be the force arising from the electric field divided by the coefficient of friction of the drops. So the ratio of the two velocities will give us this expression here. You see the acceleration due to gravity in there, the electric field strength, and the mass of the droplet. Now the Q, the charge determined for these experiments, was not the charge on an individual corpuscle, but for each droplet, only certain values of Q were found. And they weren't a continuum of values, but they came in steps. And so looking at the steps between these values, the smallest difference between them, the size of the steps, was the same whichever droplet Millikan or his students were looking at. And Millikan surmised that this value was the smallest chunk of charge it was possible to get. Millikan's paper giving a value very, very close to the one we now use for the charge on an electron was called determination of the charge on an ion. Every substance you could make a cathode out of ejected identical cathode rays. Things with exactly the same properties, whether you called them corpuscles, quanta of electricity, or just an ion, could be ejected from metals by shining ultraviolet light on them. Beta rays, which are generated by some sorts of radioactive materials, were also the same thing. These seem to be everywhere. Around about 1900, then, we had a fairly complete picture of what the electron was like. It was a tiny little particle which obeyed the same laws of classical physics as any large charged particle, with the following properties. A charge of about 1.6 times 10 to the 19 coulombs, a mass of about 9.1 times 10 to the minus 31 kilograms. Its size was basically an infinitesimal point with no size worth worrying about. Within a few years, however, experimental evidence would accumulate that required a completely different way of thinking about the electron. And one of the main pieces of evidence that eventually led there was connected with one of those other sources of electrons, that is, shining ultraviolet light on metals.